Okay. So looking at the calendar, we're going to work on section 3.1, the definition of the derivative, today and next Tuesday. And if need be, we'll finish it next Thursday. And then we're going to review for the exam. And then the exam is going to be a week from Tuesday. So I'm giving a pre-cal exam next week, and I have to write y'all's exam next week. But we should have exam practice problems in web work as well. Those will be worth bonus points on your test, but we don't do test corrections. So, like, once you're done with the test, you're done with the test. You should still review it for your mistakes because the final exam is still cumulative, so you're going to see those questions again or some version of them. So any thoughts, comments, questions on that? Yep, for doing it's probably going to be practice problems in web work. Yeah. Yeah, I know some professors do like full out practice exams, but that requires being a little more organized than I am this semester. All right. And I had to wake up early because they're installing a new door at my house. I hate waking up early. All right. So, derivatives are the big idea in calculus, like the whole reason we study this. And initially the first question is like, what even is the derivative talking about? And it turns out what the derivative is talking about is slope. So there are a whole bunch of different ways that mathematicians will say slope. And derivative is one of those. But right now, we're actually just going to focus back on the original idea of slope. But we want to think about if we have a curved graph and we want to think about the slope of the graph at a particular point. How would we even define the slope of the graph at a single point? And so when we have a single point on a curve, we can sketch through it a line that right around that point, this particular sloped line is only going to touch the curve at that point. So the rest of the curve will like bow away, flex away from the line a little. Now, if I tweaked the slope just a little, then it would actually touch the graph in more than one point close around there. So there is one magic slope for a particular point on a graph that is tangent to the curve. So we are going to try to figure out a way to figure out the slope of that tangent line. And it turns out this idea has a whole lot of applications. But let's just rewind back to how in the heck do we find slope? So what do we remember about slope? Rise over run. So those are our two big idea words that pop up. Now, when we say rise, what are we talking about? Y distances. So sometimes we'll represent this with the delta symbol for change. So change in Y, and then run has to be the corollary. So that's the change in the X distances. So if we write that as a fancy formula, like let's say I pick two arbitrary points here. So if I call that first point X1 and Y1, I call this second point X2 and Y2. Then our slope, as the formula is the change in the Y values. So we usually do Y2 minus Y1 all divided by x2 minus x1. So there's our change in y's over change in x's. All right, now we're going to take this slope formula and we're going to give it a couple of makeovers. So Chris decided a monkey with a makeover is a good picture here, which I agree, it's adorable. So what we're going to do is we're going to actually pick two arbitrary points. I'm going to call the first one A, and then the function value that goes with A can be written as f of A. That just means whatever the function formula is for f, I'm putting A in that place. So this ordered pair is A comma f of A. Just a slightly different way of writing a point. And then over here, we're calling this one x, and then f of x. Now remember, a and x here are just placeholders for arbitrary numbers. So I could make those numbers whatever I want. So when I'm thinking about the slope formula I just wrote, here's my x1 and my y1. Here's my x2 and my y2. So I'm just going to fill those in the appropriate spots. So my y2 is f of x. My y1 down here is f of a. And then my x2 we called x, and my x1 we called a. Now we were making a whole bunch of substitutions there, so I should have some parentheses. But on the bottom, the x and the a are, for the moment, placeholders for single numbers. So we could drop the parentheses there. But if we trade them out for something else, we would want to put those parentheses around whatever we substitute. So usually this formula is written without the parentheses because the assumption is if you make some substitution in there, you're going to use parentheses when you do that. So they're always kind of implied, even though they may not be explicitly written in a formula. All right, now, why do one makeover when you can do two for twice the price? So we have our original slope formula. We've got this f of x minus f of a over x minus a formula. Now, if I look over here, in place of the x, it's been traded out for a plus h. So now I will have f of a plus h minus f of a divided by a plus h minus a. But let me go back and make sure I'm putting my parentheses. Now, we didn't actually change the a, so we're okay there. But that a plus h was a new crazy thing. Now, what happens on the bottom of this fraction? Yep, the a minus a is going to cancel out. So we arrive at what is hopefully a familiar looking expression. It's definitely familiar if you've taken a previous math class here, because I know we cover it in pre-cal and college algebra. So this is what we called our difference quotient. Now let's focus in on the picture here, the graph. So when I changed out x for a plus h, Like A is some set distance, and then H is this extra distance we need to get to the position A plus H. So in this picture, like A is 1 and H is 3 more units than 1 to get at A plus H, which is 4. So I'm looking at H not as a position on the x-axis, but H is the distance, the x distance between the 2 points we're picking for our slope. So all a little weird, but making sense so far. We've just got a weird definitions of slope. And we're going to do a bunch of examples working through the algebra on this. I know the algebra can get kind of trippy for people, but we'll do plenty of practice on that. But I want you guys to get a real handle on this idea behind it as well. Because if you can understand the idea behind it, you can also get an idea for when you can use it, what this is good for. So now I'm looking at this crazy graph here, and we're going to define what's called a secant line. Strangely enough, has nothing to do with and a tiny bit to do with the trig function, but mostly nothing to do with it. It just secant means a line connecting 2 points. So it's a line that goes through 2 points on a graph as opposed to a tangent line that only goes through 1 point on a graph. So I just pick any 2 points, I can connect them with a secant line. And if I had this like working in Desmos, I could drag that secant point and move it around and the line would move with it. So the secant line can do all sorts of crazy stuff. So this is the book's fancy definition for the difference quotient. But the difference quotient is just the very foo-foo name for those 2 equations that we just produced ourselves. And those equations came from the slope. So these are just really tedious ways of saying, hey, look, I found the slope. So I can use either of these forms to find the slope of a secant line for any function between 2 points on the function. So here, we're not even doing calculus right now. This is all just algebra. So we are going to find the slope of the secant line between the given values x1 and x2 for the provided function. So our function is the square root of x. Our first x value is 2. Our second x value is 8. So our big key word here is find the slope. They've given me x values. They have not provided me with y values or function values. So I need to know what happens when I plug 2 into the function. So let me focus on the function format first. So function is f of x equals square root x. So that's the same as f of anything I want equals the square root of that anything I want. For my first point, I'm going to plug in 2. So it turns out my y value, when x is 2, my y value is the square root of 2. Same song, second verse, but for the y, for the 8. So f of 8 is the square root of 8. Now the square root of 8, we can actually do a little bit of work on. 8 is the same as 4 times 2. And I can split a square root across multiplication. So this is the same as 2 square roots of 2. So we've got here x1, y1, x2, y2. So our slope is y2, 2 square roots of 2. Now, I do sometimes get students who they might be dyslexic, dysgraphic, dysnumeric. They'll flip like the x1 and the x2 or the y1 and the y2. So I want you to just kind of look, I color coded this a bit. So the two parts coming from the second point, the x value and the y value, are together vertically, like it's one of them over the other one. And then the same with our vertical numbers over here. But then it's all in one big fraction with the difference between them. So just if you find yourself like sometimes you flip your numbers, like add this as an extra check step to it. All right, now we're just going to simplify. I've got 2 square roots of 2 minus a square root of 2. So if I have 2 ugly messes minus an ugly mess, what do I have? An ugly mess. So 2 square roots of 2 minus 1 square root of 2 is 1 square root of 2. And then on the bottom, 8 minus 2 is 6. So the slope of the line between the x value of 2 and the x value of 8 is whatever ugly number the square root of 2 divided by 6 is. So it's some positive number, so I can at least say, like, the graph is going up between these two values. And, you know, square root of 2 is less than 6, so it's not going up a lot. It's closer to a horizontal line than a vertical line. But we did what they asked for. We found that slope. So now, same kind of idea, except our function's a little uglier, and the things we're shoving in there are not numbers. Now they are variable expressions. So now we've got more algebra work. All right, so f of x2 is f of c plus h. But our function, f of x, is x squared plus 9. Now, what I like to do when I'm working with functions is I like to focus on the structure. So I do that by wherever there's an x, I scrub the x out and I just put parentheses with a blank space. So in this blank space, I can put whatever I want. I can put any number, any expression. I can put a weird squiggle line. And then my function says, whatever input you give me, For this particular function, I'm going to square that input and then add 9. So over here, when we have f of c plus h, the function structure says thing squared plus 9. In this case, our thing is c plus h. Now we're going to have to do some simplification. So we're actually going to want to algebra this out. C plus h squared is going to be a FOIL setup. So c plus h times c plus h, first, outer, inner, last. So c squared, a ch and another ch, and an h squared. So we have c squared plus 2 ch's plus h squared plus 9. So we also want f of x1. x1 is c here, so this is f of c. Function says do input squared, so we're going to have c squared plus 9. Now I'm going to go back to my slope formula. So f of x2, I figured out is my whole crazy thing that I wrote in pink. Now I'm substituting this whole expression in place of f of x2. So I'm going to use parentheses. Anytime you make a substitution, just get in the habit of wrapping it in parentheses, safe math, so you don't make any mistakes. So there's my f of x2. Minus f of x1 is this result I got in green, c squared plus 9. And I also wrap it in its own set of parentheses. On the bottom, my x2 was that c plus h. And my x1 was just c. All right, do the pieces all make sense, like where we put them in there? Now, do you see how the parentheses are playing a really critical role here? If you don't have the parentheses around the c squared plus 9 at the end, you're not going to see that that minus sign needs to distribute through. But it turns out our first two substitutions, f of x2 and x2 itself, like the parentheses around there, there's nothing being multiplied. So we can just drop those parentheses. Let me see if I can. Yes. So we have minus c squared and minus 9. And then on the bottom, c plus h minus c is just going to leave us with an h on the bottom. Now we're going to go look for terms that cancel. So we go all the way to the end. Everything from the f of x1 is going to cancel with something. That is how the difference quotient works out structurally. So this minus 9 we got here, yep, look at that. There's a plus 9. They cancel out. The minus c squared, there's a positive c squared, and they cancel out. So our leftover results, we have 2ch plus h squared all over h. Now notice with our leftovers here, everything on top has an h. So we want to cancel that h out, but now I know some people, it's like really tempting just to cross off an h on top, cross off an h on the bottom and be like, that's fine. And as long as you do it correctly, sure, but it's really easy to make a mistake there. Technically, when you cancel, the outermost operation should be multiplication and division. So I'm going to factor an h out of the stuff on top. So that'll leave me with 2c plus just a single h. If I distributed the h back, h times 2c is 2ch. H times h is h squared. So those are equivalent. Now this h that's been factored out and this h on the bottom. My outermost operations are multiplication and division. Now those can cancel. And that is my difference quotient for this function. So that is the slope, the formula for the slope of the secant line for some arbitrary value of c and some arbitrary value of h. So if I knew c and h, I could plug those numbers in there and get the slope of the line between those 2 points. So again, there's absolutely no calculus here. This is all algebra. And it's a whole mess of algebra. All right, so now we're going to do the same thing again, but the function we're working with is a square root one. So this one is going to require some algebra work to simplify it. Like even more algebra work. We do have an extra caveat in our setup. They say, oh, c has to be greater than -2. And the only reason they're telling us that is because we had a square root function. If we picked a c value smaller than -2, then I'd be trying to square root a negative number and it wouldn't be a point on the graph. It should also be stated here that h is positive, but that is just a assumed fact that comes from the definition of the difference quotient, kind of. All right, same song, second verse. A little bit louder and a whole lot worse. So rewind, let me focus on the function. So f of thing is the big square root of whatever the thing is plus 2. So the first thing I'm going to focus on is x2 when my input is c plus h. So I put my parentheses around my substitution, but there's nothing being multiplied to that parenthesis, so there's no distribution step I need to worry about here. So I could just write this as the square root of c plus h plus 2. Now for our x1, that value is a c. So now we just have the square root of c plus 2. Now we're going to go to our slope. So f of x2 minus f of x1 over x2 minus x1. F of x2 is our c plus h part, so we're going to have the square root. Sorry, let me use my colors. So there's my x2 value and my f of x plus 2 value. And then I put minus signs. And then my f of x1 is the other square root, just the square root of c plus 2. And on the bottom, this is just c. So the bottom, at least, we're still seeing our nice, oh, look, the c's cancel and we just have an h on the bottom again. That pretty much happens every time. But now we've got a pair of square roots that are being subtracted. So that minus sign does not distribute into the square root. Like square roots aren't that nice. So there isn't a way to interact these square roots in the format they are right now. But we do have a way to keep working on this so we can eventually cancel that h out. Because the whole point of the difference quotient is you do some algebra magic and eventually that h that is on the bottom by itself cancels somewhere and then you have a final result. So there has to be a way to do this. And in this case, since we have ugly square roots, this is where we're going to use the conjugate. So we are going to multiply by a very crazy form of 1. So I'm going to have all my same square roots, c plus h plus 2, and the square root of c plus 2. But what I had over here was a minus, so in here, I'm going to put a plus. So on the bottom, we just have that h times this crazy mess. On the bottom, don't distribute through. Our goal is to get that h to cancel. So the bottom, we're just going to write those two guys side by side. So I'll have my little h out front times but now on top, things get a little more interesting. So when I multiply by a conjugate, what I end up with when I do the FOIL is my first times my first. That's going to be that same square root times itself. So when we multiply, we'll have the things squared. So we'll end up just with the c plus h plus 2. That's our first term. Our outer term and our inner term actually end up being the same thing. So it's the bigger square root times the smaller square root times the bigger square root, but one of those products is positive and the other is negative. So our outer and our inner pairs are actually going to cancel each other out. And then at the end, from our last times our last, it'll be negative, and then the square root of c plus 2 times the square root of c plus 2 is the square root of c plus 2 squared. So let me write this one. So like technically this one here too is also a square root squared. So like we can see on that first one, the square root and squared are going to cancel out. So we're just going to have the c plus h plus 2. Those two pink terms are the same two square roots. One's positive, one's negative, so they are completely gone. But then over here, I have minus the thing squared, the thing being a square root. So we end up with minus c plus 2, but there's still some parentheses around the c plus 2. Because that minus sign that's outside the square root applies to the whole thing. So the square root is gone, but that minus sign still has a distribution setup. And then it's all over the same crazy mess. Now this minus sign here, though, we're going to end up with a minus c and a minus 2. And oh, look, there's a positive c and a positive 2 on top. So all we end up with on top is an h. And aha, there's that h on the bottom. So those h's cancel, and we end up with a final result of the square root of c plus h plus 2 plus the square root of c plus 2. Um, so right now, because we can, but what we're going to see, we're going to add calculus to this in a minute. So when I have the 2 points, the x point and then the x plus h point, like if I say, I want to make my each distance a little smaller. What if I make it a little smaller and a little smaller? Like what is happening to my points? They're getting closer together. So what did we call it in calculus when we started getting really, really close to something? Like the thing we've been studying all before this. Yep, the limits. So what if I actually made them the same? Like what would my h distance be if those 2 points like ended up on top of each other? 0. And then in this setup, I'd be dividing by 0. And I can't divide by 0. So the whole reason we're going to all this ridiculous effort to get rid of the h is because eventually we're going to have the calculus step where we shove in 0 for h because we're taking a limit. And so we have to do this algebra so that way when we plug in the 0, we don't get bad math. So that's good. You're thinking about overall, like, why do we go to all this effort? It seems very pointless. And it does. Like, this is a very tedious amount of work. And we're going to take an exam where you have to show me the tedious amount of work. And then right after the exam, we will start learning the shortcut. And this always begs the question, why can't we just learn the shortcut? Because I had to suffer through this, so you do too. I don't know. Presumably there's some logic behind it. I can't even really defend it. Really, it just comes down to math teachers had to all suffer this torture and we inflict it on everyone else. Now, is that the answer? Hmm? Did everyone else hear what she's saying or mentioning? What's wrong with what I wrote? Now, why did I do that? Like, it's absolutely wrong. I need to put that in, but I want you guys to think about, like, why did I make that mistake? Hmm? Yes, actually, people do this particular thing quite a lot. But it's a very easy mistake to make because I canceled those H's before, but we need to preserve that this crazy mess that I have left over is still in the bottom of a fraction. So even though the H is canceled, structurally, I need a 1 as a placeholder to hold the fraction bar to show that these guys are actually on the bottom. Is also to see how awake y'all were. Some of y'all are awake. But, and I know it's a big ask. I know this is not an easy thing to do and it takes practice to do. But as you're writing down the examples, like I want you guys to have the time to think about what you're writing as well. So it's not just a blind copy, like, let me write down all the crap she did. Like, I know sometimes it is like you're just trying to get it on paper so you know you have it. But remember, I'm recording these, so you can always come back and rewatch it. But it's to think about like, there's a lot of work going on in here. I'm a little less likely to make an algebra mistake than y'all, but I can still make them. And mistakes are just a learning opportunity to not do that later. So that's part of why sometimes I will make deliberate mistakes. Like here, I got to that and I was like, this is 1 over. I'm like, I'm not going to write the 1 over. I'm going to see what they're going to say. Now, that being said, it's kind of a dick move when I do that deliberately because it's like setting you guys up to have to question what I wrote. And that is asking you guys to be very brave. I hope thus far I've demonstrated that I'm not a teacher who will bite your head off for correcting my mistakes. But I know in some classes, some teachers will get all bent out of shape if you dare say a word. So I just want to like put it out there. I recognize how dangerous that can feel, especially in a math classroom. Like it really only takes one bad experience in your past and you're like, I am never saying anything in math class again because I never want to feel the way I felt when that teacher ridiculed me. And then later on, it turned out I was right and she had made a mistake. So I am perfectly capable of making mistakes. Please ask me. I'm also very, very likely to like get overexcited and move too fast. Please make me rewind and slow down. If I ever give you guys a funny look because you asked me a question, it's because I'm trying to parse what you asked. Like I have ADHD, so sometimes it's literally my brain hasn't fully caught up with the words that came out, but it's also I'm slightly hard of hearing, so sometimes I'm literally like, what was the sounds together that made the words? So if I ever give you a weird look, it's not that your question is bad, it's that I'm trying to get my brain to process what you said. And also like when you're confused, sometimes it's hard to say what you're confused about because you're confused. So sometimes it's okay to just be like, what happened in the middle? And I'll be like, which middle? The top middle, the middle middle, the bottom middle? Like, let's figure out where middle we're talking about, and then I'll zoom in on it. So no such thing as a bad question, only bad teachers. Okay. I totally just said teachers were bad, not students. All right. Now this one pops up in our web work, and this is going back to honestly, like even like we cover it in college algebra, don't get me wrong. But like when you first learned this, we're talking algebra 1. So that may have been eighth, ninth grade, maybe seventh grade, I don't know. So when I know the slope of a line and I know a point that that line goes through, I have two pieces of information about a line. that is enough to figure out the equation of the line, the formula that would produce all the ordered pair points for that line. So there's a couple of different ways to do this. Some teachers will only use y equals mx plus b, and they make you solve for b and then write the equation at the end, and that's totally fine. That works. So y equals mx plus b is one of our, like, when people say equation of a line, that is usually like the initial knee jerk, like, yes, that's the equation of a line. The other one that you may or may not have seen before is, it's technically like a bastardized version of the slope formula. We have y minus y1 is equal to m times x minus x1. So if I think about it's like I just took this thing on the bottom and I ended up multiplying by it. So that's like, most people like can reason their way to the slope formula pretty well. Like, you guys have done slope enough, that one's more familiar. Remembering the point slope form, especially if you've never seen it before, can be kind of awkward, but it really is very similar to the slope formula. It's just the x's got multiplied, so they're being multiplied next to the slope. All right, so they gave me a slope of 7. So I'm going to shoehorn in 7 in place of the m, but save math. And then our point is 1, 2. So that is x1 and y1. So we're going to put a 2. So it's y minus 2 is equal to 7 times, and then it'll be x minus 1. Now, technically, that is an equation of a line. And on the test, that is an equation of a line. Don't do the extra work. If I don't say, write this line in y equals mx plus b form, that is a perfectly fine place to stop. Web work, though, is a persnickety little bitch and won't take that. So for web work, we'll do a little more cleanup. We'll distribute that 7 through. I don't like that. So we'll still have the y minus 2 here, and it'll be 7x minus 7. And then last step, we'll add the 2 to the other side, which will be like terms with that 7 part. So on the exam, I am perfectly capable of following your work. If you give me the point slope form and then start doing your algebra and maybe make a mistake in your algebra, if you wrote the point slope form right, I'll like box it and be like, yes, you did the thing. Now, the other way to do it, like, some people just really prefer this way, and I don't want to say it's wrong. It's not. The only reason I like what I did here is my answer at the end is the thing I'm like finishing my line of work with. This other way, you actually have to like do an extra step where you fill in and write the equation of the line. But in this setup here, I've got an x and a y value. So I can fill in 2 for the y, 1 for the x, and I know my slope is 7, so I can fill in 7 for the slope. And now I'm just going to clean this up to solve for b. So we have 2 equals 7 plus b. We minus the 7. And we arrive at b equals -5. So then our last step is to go back to our y equals mx plus b. We're going to fill in that 7 for the slope. And then we're going to fill in that -5 that we just got for b. So just a slightly different way of arriving at the same answer. No right or wrong way there, just some people only learn it the first way, and that way still works. So we do usually ask you to write the equation, like we're going to have you guys do a whole bunch of work to figure out the slope of a tangent line, and you're going to have the point where that line is, and you figured out the slope, and then we're going to say, so what's the equation of this tangent line? So you're going to have these two pieces of information, and you've got to use one of these two processes to work it out. I got to pester my colleagues to see if we're going to give you guys the equation of the line or not. This one is the one where it's like hit or miss whether they'll agree or not. So I'm just going to put it out there that you might have to remember the equations here, whichever way you want to solve it. Because for most calculus teachers' mind, this is an algebra thing. You should know this algebra thing. And I agree, but I also don't want you guys to lose points because you misremember a formula. So I will certainly be more lenient in the grading as long as in your work, like you show me, I think this is what the formula is. So I put the pieces in and I got this equation, then I can be like, all right, -1 point because this isn't the right formula, but you did try to do the thing. And if you'd had the right formula, this would have been perfectly fine. So you're showing me you can follow a process, just that your memory isn't the best for formulas. So this slide, just summary of the same things we did. And then Chris's tip here at the end, like some questions in WebWork are going to just ask for the slope. Some of the questions in WebWork are going to ask for the whole equation. Pay attention because it's not even like a whole bunch of slope and then a whole bunch of equations. It's all kind of mixed together. And it can be really frustrating to get the slope. You did the slope right. And you guys know how error messages are on WebWork. They make no sense. So you type in 7 and they're like, error, you should not be typing in a decimal. I didn't type, what are you talking about, WebWork? Huh? So easy mistake to make that's not a mathematical mistake. It's a WebWork, like reading the question mistake. So just be on the lookout for that. I didn't think we were going to get here. So let me see if I can't type that in. AHVINOLHKT. Yeah, let me flip the share to this. So we have here a function, 3x squared minus 5x plus 20. We have an a value selected, and we have an h value selected. So the a value is just some point on the blue graph, and it fixes it as like x comma f of x. And then h is changing the distance from that a value to the secondary point. All right, so initially here, I've got it set to be x equals 1. Now my h value can get really big. And then over here on the left, we can actually see the slope number being calculated. So as I slide this h around, the slope is going to change. And what we're trying to do is we're trying to actually figure out like what's the slope of the tangent line there. And we do have, that's what the dashed red line is. That's the actual calculated slope at that point, and then the equation of that line sketched in. But we're just trying to play around with our h and try to get an idea for what that value is. But take a look. When I actually put it on H itself, though, I get an undefined because Desmos doesn't do the behind the scenes crunching as well. But really, really close. I got about 1.3, 1.6, 1.9. All right, so I know this slope. And then on the other side, I got 0.7. And then 1.3. So maybe that slope is about 1. Now, I know you may be looking at the graph and you're like, a slope of 1 is not like this. A slope of 1 should be a 45-degree angle. It should. But look at our X numbers versus our Y numbers in this graph. The Y numbers are going all the way up to 60. Our X numbers barely make it to 6. So the diagonal here actually is that squashed line. Like that, for this crazy squishedness, that's a slope of 1. So Desmos can do derivatives. So down here, the tangent line equation is actually calculating the derivative of the A value. And then this is just the point slope form with the Y1 value added over. Now, if I change my A value, like how about 2? So now here, got some pretty big slopes. So we got something 7.3 and then 6.7. So yeah, maybe at 2, the slope there is 7. Like that'd be a good estimate with the way these numbers are moving in a pattern. But to get an idea of that tangent line, the idea is that we want to take our H distance and we want to shrink it down as close as possible. And that idea of getting closer and closer and closer is the calculus idea that we were studying with the limit. Because the limit is get really, really close, look at the pattern that the numbers are doing, and tell me what that looks like it's approaching. But we're never actually technically arriving at the place where they're the same. So we're just saying, like, pretending if they went there, this is what the number that would fill in that pattern would be. So here, Chris picked an A value of 1 and an H value of 3, and those are ridiculously far apart. And we end up with that green secant line is drawn between them. That slope is way off from the red dashed tangent line. So if we shrink the distance down, well, now the green line is getting closer to that red line, but still not perfect. And if we get it even closer, that H equals 0.1 that we were observing, that was as close as we could get with the way Desmos was zoomed. Like technically, we could even type in smaller H values and get even closer approximations. But here's the question that we got earlier, like, what was the whole point? And the whole point was, like, eventually, we want to let H equal 0. Like, that would, looking at our picture, that would give us the slope of the tangent line, but 0 in this equation is bad math. So how do we get around setting H equal to 0? Well, we don't set it equal to 0. We do the limit as H goes to 0. So this definition, this is the big idea in Calculus 1, is the derivative of a function is just giving us a formula for the slope of the tangent line of that function. So derivative is slope. We are going to focus the rest of the class until the very last week and a half. We'll finally look at integrals, but all the rest is going to be derivatives and all the crazy things we can do with derivatives. So the most important definition we will see all semester. It really is. Now, technically, either these two definitions are equivalent. You could use either one. Most of the time, and most examples you will see online, most people use the second one where it's the limit as h goes to 0. I don't know, just the older books would only explain it from this perspective. So we didn't always use the x minus a perspective. Technically, though, either one works. And there are a few problems where the limit as x approaches a is actually easier to work than the limit as h goes to 0. The difference is the first one, you eventually are trying to cancel an x minus a factor out of the top. So to use the first definition, you have to be comfortable with factoring. And that can get kind of ugly. Just depends on your comfort level with doing factoring. The bottom one, the algebra can get a little uglier, but the thing you're canceling out is just an h. So seeing, all of these have an h, sometimes that's easier to see. And then typically, the questions where the x minus a method works are with polynomials. So this is like the case where this way will work out okay. So a lot of your homework for 3.1 is going to be find f prime of a for f of x blah and a blah. Or there's a caveat, state that the slope is undefined. We can't actually have points on a graph where the slope is a vertical line. And a vertical line has undefined slope because it's all rise and no run. Most of the time, though, we're going to get a number. Undefined slope points are actually pretty rare. All right. Let's go back to a real pen. So f prime of a is the limit as x approaches a, f of x minus f of a over x minus a. So let's fill in some of the numbers we got. We got 10 for a. So now this is the limit as x approaches 10. We still have f of x, but now we have minus f of 10 over x minus 10. So f of x is just the function itself, the 12x squared minus 6x minus 7, minus f of 10 We're going to have to do the same thing, but we're going to shoehorn in a 10, and that's going to equal to some number. And then that's all over x minus 10. All right, so I know we're going to still have 12x, sorry. Now, this is one of the things that happens when you're writing is you get so focused on the algebra, you forget, oh, wait, this is a calculus thing. And so you have to go back in and squeeze the limit in. So if y'all forget on a line on the test, like I'll write it back in for you, not the end of the world. But technically, we are supposed to write it on every line. All right, so we've got 12x squared minus 6x. So can someone crunch up what that number ends up being, the blue part? So we have -7 and that. So it's like the blue part is that, and then we have the minus sign from the formula, yes? Is that what you meant? Or was that after the 7? Yeah, it's 1200 minus 67. So what is that, 1133 then? So we've got -7 minus 1133. So we're going to like add the 7 back. So it's minus 1140. Yeah, -7 minus 1133 is minus 1140. There we go. So it turns out with the way the structure works here, this thing on top has x minus 10 as a factor. So I am going to take a leap of faith and assume that that is a factor and write what the results would be. And then I'm going to check and make sure it actually is. So I have an x. I would have to multiply x by 12x to get a 12x squared. I have minus 10. So I'd have to multiply -10 times positive 114 to get negative 1140. All right, so my first x times 12x is 12x squared, but I want to check my outer 114x and my inner, which is negative 120x. And yep, that's negative 6x. So that is the correct, like this is our side thought bubble. This is the correct factoring. My x minus 10s cancel out. So now my line work says the limit as x approaches 10 of 12x plus 114. Now what do we do? Yep, we plug in 10 because we're just doing a limit. This is a nice continuous function, so we can just put the 10 in there. So 12 times 10 plus 114. So it's that 234. So a slope of a huge number like that means this line is almost vertical. But we were also at an x position of 10. Most of the functions that we study in calculus like make their vertex of the parabola pretty close to the origin. So like this tracks. When you move far from the origin, the graph is just shooting way up to infinity. That's what that slope is telling us. This graph is going up as like not as fast as it could. There are graphs that will go up faster, but going up pretty fast. Doing it as hard as it can. I just want to contrast that work we did with the x minus a format for the work we did here with the x squared plus 9. Here, when I put in the c plus h, I had to FOIL out the c plus h, and then I had the minus f of c, and I had some terms cancel, and the h's were all in common. I factored it out and canceled it. This one, I'd be doing the limit as h goes to 0. I'd plug in the 0 for the h, and I'd get 2c as a formula for the slope of this graph for any arbitrary c value. Like that is one of the things we can do with these formulas. But the initial examples, they have you plug in numbers. So this second example is giving us two different a values, and they're rather disgusting a values. Now, maybe they work out nicely inside the formula, but well, yeah, the 5/9, we'd actually get the square root of 0 out of that, so that's not horrible. But the 23/3, 3 times 23, 69 minus 5 is 64, so it square roots nicely. But we'll tackle this one next class. But the other thing we can do here, especially when they're giving us multiple points to plug in, instead of working out the limit for each individual one, we can work out the derivative formula in general and then just plug those values into the formula. So you do have a writing assignment. Let me, oop, no, this one. We have a writing assignment that I forgot to publish. So here, let me show y'all real quick. HTML. All right. So the HTML actually rendered decently here, but there is also a PDF link if you just want to print it out. You can also just write down the two functions and figure it out. But this first one is giving you a piecewise function. And they're asking you to, like, what's the requirement to show that f of x is continuous at 3? Like, what do we need to be true? So if you look at the definition from continuity that had a, like we need the limit to exist, we need the function to have a value, and we need those two things to be the same. So the requirement is like that third step, like they all got to be the same. And then you're going to use that requirement to figure out what the a value is here. Hopefully there is an a value because I actually forgot to work it out. And then the second question, totally independent from the first question, is asking you to find the end behavior for this weird, wacky rational function. And really what it's asking you to do is just evaluate the limits as x approaches positive infinity and then also do the limit as x approaches negative infinity. So just two infinite limits on a little polynomial there, and then a weird kind of play around with the definition of continuity. So if you get stuck, like, how the heck do I start this? Like, what did she mean with this question? Like, feel free to hit me up on the GroupMe. I can help you guys like understand the structure and what I was trying to communicate. Because sometimes when I write questions, I think it's straightforward, and then everyone else is like, this makes no sense. And I'm like, whoops. So I think I worked it out enough.